This is our latest EV webinar. This one's going to discuss high voltage batteries and technology related to that. Leading us and taking the lead on everything is our EV expert, Mr. Dave Giles, along with our Director of Education, Nathan Bakey. And as I mentioned, if you have questions, we want to answer them. Go ahead and drop them in the Q&A portion on Teams, and we will read them toward the end. What we think this is about 20, 25 minutes, Dave?
Yeah, a bit 20 minutes. We're going to try and make sure we have some time for questions. So,
well, then with no further delay, go ahead and take it away.
Sure. Okay, great. Well, I'd like to thank everyone for joining us today with our ConsiLab webinar series on high voltage batteries. And today we're have a few different items here. I have a desktop beside me full of components and stuff, which we'll show a little bit into, as well as we'll give you some ideas on talking about high voltage batteries in the classroom. Also, we're going to talk a little bit about the, I know this is a big subject that's been coming up. I've been seeing on the forums about arc flash protection. I'm not going to get into great detail, but I'll talk a little bit about that. I'll talk about an incident that happened at an education institute that involved a high voltage battery just recently. So, but anyways, we want to get going with our series on here on the batteries, and I want to thank Nathan for joining as well, and he's got a few things to show as well today. So, I think I reduce my screen down here a little bit.
So I was actually going to start with a suggestion, idea, and demonstration for anywhere from high schools up to your college level programs. And this is probably something that many other schools have already done. But for those of you that have never done so before, if you've never taken apart a 9-volt battery like this here and looked inside, because we talk about high voltage batteries and we have the term battery. And the term battery could be anything from a single cell like this here, up to the entirety of a battery pack of an EV. And one of the easiest ways to relate this for a student, I find, is if you take something like the 9-volt battery, like this one here, and you strip it back and you look inside. On a regular 9-volt battery, there's a couple different versions. You'll find this is a cool stacked cell. And then other ones, when you take them apart, you get these little tiny battery cells themselves, which are the equivalent of a 4A battery. And it's something that's very inexpensive, very easily attainable for the school if you don't already have them in stock. Low danger, because even if you lick the terminals across a 9-volt battery, you won't get hurt. And it's something that your students, if they take apart a 9-volt battery, measure the individual cells, do the math and bring it up. Okay, well, what is each cell? How many cells are there inside of this? That's actually a battery module. And you can relate it to them that how we build up voltage. You know, the chemistry stays the same. The battery cells stay the same. It's the configuration and how they're really put together. And then try to relate that, that's what we'll talk about in a little bit, is try to relate that to what they're going to see at the other end of the spectrum, which is when they're on a scan tool, looking at scan data and seeing pack or module or whatever term is used for the voltage. So I just thought I'd share that with you. If you're not already doing that, if you've never taken apart a little tiny 9-volt battery, I welcome you to do so. It's a lot of fun.
And that's a great example that Nathan gave, because as we move on, just give that example. Here's a nickel metal hydride battery, and you can see in that is very clear. It's not one like on a 9-volt battery that Nathan had there, similar to that one. Each one of the little wafers in there or the cells is about 1.5 volts. In this pack, they're 1.2 volts, so about 7.2 volts, and then they're put in pairs to give your 14.4, 15 volts, which you probably see on your scan tool, and they break these into, modules within that pack. So, so the thing is we'll be looking a little bit at that, because obviously the lithium-ion battery is very unique because it has way more energy density, and we'll talk about the energy density and the construction there. But Nathan had a picture of a battery. You want to put that battery back up, that little lithium battery?
This one here?
Yeah, I just noticed what it says on it.
Yes, this is a cheap off-brand one. It's not. I don't recommend buying ones that are named Ultra Fire, because That leads on to other problems you don't want to get into.
But anyway, so I just thought it was kind of comical to see that on the side of a battery. So we're going to get started here. High voltage batteries and systems in EVs. We talked a little bit last week about our gloves and some of the things about the gloves. We talked a little bit about isolation faults, loss of isolation, and moving in through some of the tools themselves a little bit. We'll get more into that as well today. Testing high voltage systems, like I said, incidences that can be reduced in the classroom, as well as in the shop if students are working around a high voltage system in a vehicle. Essentially, that's a pack there. We call it a pack. It holds modules, which holds many cells. Cells can be in different configurations. They can be in a pouch cell. They can be cylindrical. They have here cylindrical cells, and also you can have them in in different forms as well, depending on the manufacturer of the battery. And so the prismatic cells, that's what I'm trying to think of there. But essentially they're all pushed together into this big module. This module on this vehicle weighs just under 1,000 pounds. So be aware that, they are intimidating looking because they're so big, and it covers the entire bottom of the vehicle in most cases, but it holds a lot of energy, and that density is broken down. If you keep going down, you can break down the high voltage battery just into individual cells. In fact, here is an individual cell from a Tesla. This is a 2170 cell, so about 5 amp hours nominally for that cell. So we 3D printed these. So sometimes if you have a 3D printer in your school, you can 3D print these. There's some files online that makes it easy, and they're just like, basically a 3D printed 2170. I have some 4680s, 1865s, and they're great for passing around. They can measure and see the size of them and how they're configured. So removal of a high voltage battery, first off, from a vehicle has a lot of processes and procedures, and it's ensure the safety in removing that high voltage battery. But you gotta remember, any of the disabling features of the service disconnects and so on within the high voltage battery does not eliminate the risk of high voltage being removed from that battery. We can knock the battery voltage down, hence what our disconnects do, our service disconnects do. I'll explain that in a second, but just got to remember that energy is still held within that battery and within the cells and the packs, or inside the modules inside that pack. So very important that you always treat the batteries with respect. You have the proper equipment to lift and lower these batteries. The standard is usually around 2,500 pound lifts requirement to lift these. Most batteries, I haven't seen a battery go past about 1,400 pounds. But there is new packs coming out, bigger packs. I was just down at Rivian in Ontario, and they're running 146 kilowatt hour batteries. And they're definitely going to be a lot heavier than this typical 85 kilowatt hour battery. Okay. So the different types of batteries, as I mentioned real quick there, we have our cylindrical cells. The big difference between this battery and the nickel metal hydride battery is the voltages. So this is about 4 volts. This cell here, the cylindrical cell, they're 3.7 to 4.2 volts. But this one here is 1.2 volts. And just like in our 9-volt battery, it's, basically 1.5 volts. And in a flooded lead acid battery that is conventional is about 2.2 volts. So once again, different voltages, different capacities and energy, which makes them very unique for each of the applications. So obviously this one cell is equivalent to probably about 10 of these nickel metal hydrates in energy capacity. So it's quite amazing how much energy density is inside the lithium ion cell.
Now, it's really interesting to know at the chemistry level and at the cell level what's going on. But we have to also, consider that when you're working on the vehicles, you never get there. And a technician would never get the lowest level that a technician working in the field would ever typically get, and this is getting very far, is to a module, right?
Yeah, modules. Cells, the reason Nathan's correct is these are two cells from a Tesla. And in order to remove the cells from the modules, you actually have to smash the modules apart. And I'm using that term very loosely, but they really do. There's no replacing broken cells or bad cells. They're essentially they're glued in place. There are no way you can tear these apart and just replace a bad cell that has failed within that module.
Yeah. So.
Okay, so just give that in some modules, but not saying all of them. Some of them we can get down to the cell level, and in the sense here, I can't replace just this, but I can replace this module. And there is some aftermarket ones coming available. This is from your Priuses and your Chevy Tahoe hybrids and so on. So, and then and even in these guys here, this is from a Nissan Leaf. This is a cell. And there would be 3 in this one module, but once again, I cannot take apart that module and just replace one of these cells. I have to replace that whole module. Okay. Moving on. Okay, so a lot of people ask me, they talk about the cell size. So I'm talking cylindrical cells here, the examples of this one here. And the size of the cells, they call them 2170s. You may hear of the 1865 zeros. But essentially, all they are is the size of the battery. These are Panasonic batteries that are on the screen there. This is a Tesla battery made by different manufacturers as well. But the case itself is a standardized case. And when they talk about the numbers, a 2170 is what this cell is. That's 21 millimeters across the top and 70 millimeters down the side. And that defines the cell and what it is, just like our AA batteries and AAA batteries and Ds and Cs. I could have a Energizer battery, I could have a Duracell battery, but they're all AA's in that size. So same thing here. It's what's inside the battery that makes up the chemistry. New batteries that are coming out in the lithium field contain very little and no cobalt in most cases, using a lot of graphite materials. And now batteries even are using sodium. And what sodium does, it reduces the risk of thermal runaway with inside the battery. So, once again, it's not as powerful of a battery, but it definitely has a lot more safety features within that battery. So we're going to see a lot of changes happening within the chemistry. The chemistry in a battery, and I live in Nova Scotia, and not even about 4 kilometers from here is Dalhousie's lab. And Dalhousie is a world-renowned scientific lab for battery research. In fact, Jeff Don, who basically comes up with the chemistries for Tesla batteries, he's right here in Halifax. So, and that chemistry is always changing. They're always testing these batteries. They're always running through new materials and different configurations to obtain the maximum amount of power from a cell and be able to do it safely as well and consistently, and increasing the cycle times within a battery. Okay, so like I said, cells are made into modules and modules are put into packs. So example would be this nickel metal hydride. We have our individual cells put into a module. Modules are then put into packs. And that's how they start to build the high voltage batteries in the packs. In fact, I have the Tesla. Tesla has 25 of these configuration, these modules within a sealed pack, or within the module itself, sorry. And every one of these so there's 2 plates, and they actually go.
Do you want to maybe go to the next slide, Dave, that you had the Tesla battery? We can use that as an example.
Sure.
I think it's
there. You go. There's the example.
So as Dave holds that up and lines those up, those metal strips are what configure the cells. So at the cell level, I'll let him explain how they're connected, but as he holds it up there, if you've ever, for those of you that have never taken apart a Tesla battery, so on the PowerPoint slide, we see 4 main sections to the battery. That's the entire underside of the car. Each one of those 4 sections houses a battery module. in which you would have however many hundreds of batteries of cells.
Thousands.
And yeah. And for each subsection of that, because each of those is 100 volts, going up to the 400 volts pack voltage. And then inside of each one of those, if you look where it's kind of yellowish and metalish in between the green, that's what Dave's holding in his hand. This is what puts it together, the cells in series and in parallel at different points in the pack.
So the way they work, and Nathan's correct, so there's 96 of these cells in each one of these groupings. So there's 96 of these little cells that they're attached here. And on the top of the battery, I have one here actually. And this is the one we just recently, I'm sending these off to the lab to be done. But on the top, you might be able to see there's a little tiny nipple on the very top of this battery. So inside this battery in the very center here is a positive. And on the outside here, this outside edge is a negative. And what they do is on here, you might be able to see this, you'll see these little tiny little wires hanging there. They're actually act as fuses as well. And essentially this would touch the center of this terminal here on the battery. And then on the outside edge, there's another little nipple there where there's another little wire here, which is on the opposite plate, which attaches the negative. So that's why when I was holding them up here, I had them in between like this, because essentially this battery sits kind of like, one side will be touching almost a negative and the other one will have a little wire going to the center. So when I measure it, if I measure across these two, because these are in parallel, I measure across these two, it's only 4 volts. But there's essentially 96 of these cells in each one of these legs. I call them trees. And, essentially that gives me my energy density. Yeah. So that gives me my amp hours in that battery.
Yeah. And then you have 20. So of the 96 in that branch tree, all of those are in parallel 4 volts. And then you've got 25 of those per each one of those stacks in the battery.
Yeah, that's right. So each one of these groupings, there would be 25 of them, which gives me and especially on the longer packs, there would be 25 of them, which gives me my 100 volts nominal. So that's how they're constructed. So if you ever had a chance and you were able to tear down a battery, you got to remember when you're going through the battery. I think I have a slide here. Actually, it's going to go one slide first. Here, you can see in this picture here, you'll see that there's a positive plate, and then there's the negative plates right here. So once again, so you can see how the wires are. You can see each cell here, and how this little wire here is in the center, and then on the edge would be the other wire. So it's building this pack. So in fact, if I went to this pack and put my hands directly on this high voltage battery pack in these two areas, I'll only have maybe maximum 12 volts. So it's as I start to move down the pack, the voltage starts
gets more dangerous.
And it gets a lot more dangerous.
What's important for me is that it's really important to understand that level of pack structure. But I think that the correlation for students, for technicians, and for instructors of understanding how far do they get in the data that they get from a scan tool, and being able to relate that to something tangible. So if you're in a scan tool on a Chevy Bolt or on a Ford or on a Tesla or whatever it may be, and you're pulling up data on the battery and you're seeing individual voltages, to me, it would be very important to understand, okay, if I'm able to get the data PID of that voltage, that represents 15 cells, 500 cells, 1 module, 10 modules. At what level is that? And again, this is more for the teaching and understanding sake. Most technicians are not, at least right now, getting that far into there, and the pack disassembly like that is not recommended and not something that I think a lot of schools are going to be doing, because that's where the inherent danger is omnipresent. That's where the wrong mistakes, that's where you need the arc flash and all of the protective gear, because even when you're trained and you're in a lab setting, you can still make a mistake and have significant consequences.
Yeah. And great points, because in simple 3D printing, you print off a whole leg of these, print off, a configuration, and even have the students build and construct, how do you get 48 volts out of 4-volt batteries, or, have them come up with some ideas and how they can start building their own high voltage batteries. In fact, and Nathan mentioned earlier when we were just prepping for this, talking about flashlight, flashlight uses 4 D cell batteries, so 1.5 volts each battery, so as you multiply them, you get higher and higher and higher voltage. So the question I remember was asked is, if I took enough AA batteries and tied them all together, could it be lethal? And sure, it can be. If you have enough of those batteries, once you start crossing those thresholds, now you're into high voltage, and in that high voltage requires special protection, processes, and procedures in order to handle and work with them. So
enough of these little 9-volt batteries, you can strike an arc with 10 of those in line. You can get a stick welder going for a short bit of time.
Yeah, well, that's right. Your stick welders are 20 volts. It's so an arc welder is not very much voltage. And when you're talking about 600, 400 volts, and you see the arc that comes from a stick welder compared to when you're dealing with 400 volts, and yes, and you have to be aware, and that's the biggest thing. You can't take it for granted, and you have to be aware of it. And one of the things I want to make a very good point here is, because I work closely with one university has 2 different types of labs in it, and they have what they call cyclers. And what they do is they cycle the high voltage batteries for how many times. They do it in vacuum under extreme temperatures, hot, cold, so on. And one of the things that comes up, and you'll see this on scan data as well, is cycle time. So there would be a PID there, probably under seeing cycle time. And cycle is how batteries are measured for their longevity. So we talk about degradation, as a battery degrades, can't be recovered. It's based on fast, people say fast charging, overcharging, mileage on the vehicle. Cycle time is very important as well, to be able to aware of it. Our cell phones are, good for about 150 to 300 cycles. That means full discharge to full recharge. So if you have your phone at 50%, you charge it to 100, and then you discharge it back to a 50%, then basically, you're into a cycle. So it's like one full on, one full off. So it has to be 100% in doing that. So if you take your phone down to 0%, charge it to 100, and then, and then take it back down to 0, you have one cycle on it. And cars are the exact same way. Electric vehicles can get anywhere from 1,500 to 3,000 cycles on their batteries. And one thing I want to make a point, the battery technology in your cell phone is different technology that's used in a lithium-ion battery in a vehicle. So be aware of that. So some of these manufacturers of the batteries, depends on how they're built, they're a lot smaller to fit in the phones and stuff. So, they don't have as much cycle time, but also they are a different type of chemistry within some of these lithium batteries. Not all of them, but most of them are very different chemistry. Don't ask me why they don't go to more advanced technologies. It could be cost and whatnot. But saying that, if you look at the cycle time on a battery, electric vehicles, 1,500 to 3,000 cycles on a battery. If the vehicle can travel 500 kilometers, or it gets a charge of 500 kilometers per full charge on the battery, it might not travel 500 kilometers. You might get, maybe 400 kilometers on that charge. But regardless, it's incredible how durable and how long these batteries will last. So a lot of the stuff that's in the news, a lot of controversy, I would agree. In the early days, yes, without thermal management systems, these batteries couldn't take very much of a hit. But today's batteries, with their battery management systems and the chemistry in these batteries, they're starting to see over 1 million kilometers on their cyclers for these batteries. So they're very, very good. So we are seeing them last a lot longer. So that's that's the reassurance of what you're teaching and what you're portraying, is that these batteries will definitely outlast the car. And we're seeing cars now getting well into the 600,000 kilometers. This is Canada. Mileage. We're seeing a very high mileage coming onto these electric vehicles. So we're seeing them and with a very little degradation on them, which is really interesting. So. Okay, so it's moving on. High voltage service disconnects. So one of the things in high voltage servicing comes to these high voltage disconnects. Whenever we want to work on a high voltage system, these disconnects need to be removed and secured, and must be done properly. Some vehicles have them in different places. Most times they're on the battery. So like you won't find a service disconnect remotely located in another part of the vehicle, not if it's directly connected to the high voltage system. It's usually connected to the battery in some fashion. I always say check the EVS. There's an app that you can download. It's called EVS. I think I mentioned it in one of our other webinars, but thing is, if you can just go to the first responders guides. They'll usually tell you where they're located, service information, and then they'll give you the procedure of powering these things down, ensuring that the high voltage is reduced. And I say that reduced. It doesn't eliminate it, and the threat is still present within that battery. These high voltage disconnects, what they do is they break the tax voltage. So, which means if I have 4 big modules in that pack, and I pull that the service disconnect, and each module is 100 volts, essentially I break the series of that pack, which reduces it down to 200 volts on either side, making the battery a little safer. And because it's a broken open series circuit, there's very little risk in getting a shock from the vehicle unless I start going into the battery. And that's when I would, have to be aware of the 200 volts each. So do all batteries have these? That's the big question. And you know what? I forgot to bring in my Tesla one. But
they definitely don't.
No, they don't. Tesla uses a pyro fuse, and it's not easily accessible. So their procedure is in different cases. Some of them is to unplug the first responders loop, disconnecting the 12-volt system, and then unplugging the first responders loop. That's because of the DC to DC. Don't be aware when you pull out a service disconnect plug, because of when you pull this out, you kill the pack, you kill all high voltage system components. But in Tesla, it's a little different, and you got to be careful, because if you do pull the first responders loop, like a Model X, Model S, and then newer Model 3s, they do have their ability to unplug them, don't cut them. Then what would happen is that your DC to DC, you have to be aware the 12-volt system is still alive on that vehicle. So even though the DC to DC is off, the 12-volt system is still operational. So you have to disconnect the 12-volt battery and then pull the first responders loop and then do your checks for high voltage before, servicing a high voltage component on that vehicle. So that's very important, especially when you're doing this. Do you have to disconnect this every time you're going to service a high voltage vehicle, like brakes and tires and so on? Always follow service information, but inherently, unless you're touching something with orange cables or high voltage components that's identified, these usually do not need to be removed. So.
I think time-wise, we're probably at a good spot there. Jimmy, do we have?
We're at
now's a good time
here.
Yeah, it'd be a good time for any questions that people have, if we want to be able to field some questions.
So I'll kick off the questions because I actually have one. Why do most, if not all, the EV manufacturers expect you to only charge to about 80%, and then everything throttles down at the charger after that? Is that for degradation purposes, or what is the reasoning behind that?
There's a few things. One is for degradation. Manufacturers recommend charging 80%. In fact, a lot of the manufacturers are, like Jeff Dunn will say, to maximize the most of your battery is going from 40 to 80, 40 to 80, 40 to 80. That will maximize your battery over that period of time. But also at a charging station, once you hit 80%, you should have enough charge to make it to wherever you're going. If you're on a road trip, you should have enough charge to make it to another charging station. This way it frees up the charging station as well. If they start to throttle it back at 80%, at that point, most cars will have well over 300 kilometers in range, at least 250 miles, so they're able to get where they need to go. So this way, someone else waiting for the charger can get that charge as well, too.
All right. I don't currently see any questions in the Q&A.
So I see 2 questions there right now. Volkswagen now has their disconnect under the hood and only opens the low voltage system at the contactors. Thank you for sharing that, Mr. Anonymous, Mr. or Mrs. Anonymous User. That is very interesting. I want to know which Volkswagen model. I'm going to guess ID4.
And a lot of them, and I agree that even like the Konas will have the pull plug right in the fuse box. Tesla, that's where I was getting to. Tesla, in like the Model 3 from like 2017, 18 actually, but 17 was first production year, but 18 to 20, basically you have to go back to the rear passenger side section and unplug the high voltage connector to the controller. It's right underneath the corner of the back seat, very easy to get at. And then you have to kill it that way. So yes, because what they're doing is they're powering down with the 12-volt system, breaking essentially the interlock loop, within that circuit, opening up the contactors. But once again, always test. Not that I have any reservations about those systems and how they work, because they're definitely very robust systems. But once again, since you're dealing with voltages and low voltage control of high voltage, it's always validate the voltage. And in the slide here I have on the screen, I'm actually showing that after disconnecting the high voltage controller on the vehicle, now we've gone and we've tested at that point to make sure there's no voltage present in the high voltage system there.
So our friend Claude Townsend from Oakland Community College asks, how does a Tesla condition a battery for fast charge?
So Tesla does it a couple different ways. One, it uses the electronics in the vehicle. Because Tesla doesn't have a heater in them. It's good. Like a Tesla Model 3, I'm hoping he's referring to, because the S's and that do have a heating type system. But essentially they use the electronics within the vehicle to heat the coolant, and then goes through, as well as it also loads up the stator. And that's the key thing, is that when it loads the stator up, it becomes very inefficient. So as you're going to a supercharger and you're preconditioning when you're driving on the highway, it's actually loading up the stator, making it a little bit more inefficient, but then it's taking the oil from the pump and pushing it over the stator and rotor, collecting the heat, and then puts it up by a heat exchanger. And then the coolant that runs past that heat exchanger picks up the heat and then goes back into the battery cell. So a great question, because that system uses a strategy that doesn't use any external, like a PTC heater and so on, like the Bolt, and so that that helps heat that battery. So
that's for heating in the case like where the winter months up here where it's really, really cold. But so that'd be conditioning the battery in the environmental circumstances where the battery is cold and we need to warm up the battery in order for a fast charge to be possible, because a battery that's too cold cannot receive a fast charge. On the other end of the spectrum, if the battery is
Tesla uses liquid to air condenser to heat the coolant. Is that correct?
What's that, sorry?
Somebody said Tesla uses a liquid to air condense to heat the coolant.
So what they do is so there's a couple things. When the battery is too hot to receive a fast charge, or during a fast charge in a hot environment, we have to remember the battery itself, in the case of the Tesla and many other vehicles, is cooled via glycol circuit, coolant, essentially. So liquid cooling or liquid warming in some cases, as Dave just mentioned. And then what they're doing is using the air conditioning system. so the refrigerant system, to pull the heat out of that, dump the heat out the condenser at the front of the car. And they do that through the chiller, which is a thermal transfer device, essentially, between the refrigerant system and the cooling system. So that's another way that on an electric vehicle, they would prepare the battery to receive a fast charge, or during fast charging, maintain the battery temperature. This is something that I always invite people to do. Is if you ever walk down a row of fast chargers, not the level 1 or level 2, but those big DC fast chargers, just listen. A lot of times on a sunny day, you walk by these cars, the fans are just going full pin, dumping the heat out of it to keep the batteries cool to receive a good charge.
Somebody had a bad connection. They want to know what the name of the clumps of the cells together. I think that is called a module, right?
Yeah, the cells together is within a module, and then you're within a pack. And here's a good one here too, is that in talking about that, there's this green goo or this blue goo on the batteries themselves, and you'll see them, they're packed in this gooey goo, and this stuff is actually, I even tried burning it, and actually it burns, but when it burns, it puts a protective layer and it turns to an ash, which the ash can help absorb heat within the battery itself. So, so they call it a luminescent, this product itself, and it's used in some high voltage battery packs to help with thermal management with inside the battery.
So there's another back and forth about the AC condenser. He says that's a chiller. There's a liquid to AC condenser to heat the battery through the octo valve. It will run the AC to heat the battery. Is that correct?
Yes, that is also correct. Depending on the year, you're absolutely positively correct. Depending on the year of the vehicle, I was talking about the heat pump.
Yeah. Preheat,
so yes.
Heat pumps, yes, yeah. That's why I said 17 to 20. This is how it was doing it. But you're right. Within a heat pump system, then we can start scavenging heat to help heat the coolant through the heat transfer in the octavalve to allow the heat to go in to help warm the battery, becoming more efficient, especially before supercharging. Yeah, way more efficient.
And
yes,
this
thank
is
you.
Really
yes.
Yeah. Thank you for that, because this is also very fascinating stuff. And this is the type of technology that we research at Constellab in developing products. A couple of the products that we have in the engineering lab right now are directly being developed to teach those phenomena. So, and what's cool is that we get to, Dave and I and others at Constellab, we get to research all these different possible configurations, because Nissan does it one way and then Volkswagen does it another, and Tesla is special on their own, and then you've got Ford does it another way and GM is somewhere else. And what we try to do, of course, because we want you guys to have cool training aids, is build something that's unique, generic, and that sometimes doesn't even exist in the real world. So right now, one of our prototypes for teaching that, it does all of that, but no car in the world actually does. So it's fun and interesting discussions to have. There's another prototype Dave just put up on the screen there for another product we're working on that's coming along very well for high voltage systems.
Yeah, yes. You had mentioned something about an app, and somebody was looking for it in the App Store, but
perfect
EVS.
Yeah, it's called.
I would say EV Rescue. I think we may have misspoke.
EV Rescue. Yeah, it's on my phone as.
It looks like this, does it not, Dave?
Yes, that's right. Exactly.
EV Rescue.
Yeah, EV Rescue. It looks kind of like that. I don't know if you can see my screen. It's really great because you can pick your make, model, your vehicle, and it's a complete first responders guide. But the beauty is, if you're even with charging station, DCFC from Flow, ChargePoint, Tesla, they all have all them in there. They have truck and transport as well, bus and coach, and it's all the first responders guide, and it's completely free.
We got two good questions. Someone wanted to know what the life of a battery is if a person uses only fast chargers.
That's a good question. It comes down to the thermal management of that battery and what level they're charging to. So Jeff Dunn, in one of his seminars that he did, he actually talked about that fast charging in their batteries and what they're doing is having very little effect on the longevity of the battery. So they said that the degradation, it wasn't as predicted as they thought it would be by just fast charging the battery. So, but mind you, that is staying within that range that Jeff talks about between the 40 and 80%, of that charge level. So like, fast charging to 80%, driving to about 40, 30%, then recharging, maintaining that range itself, is kind of, and he says that will maximize the battery. I fast charge a lot when I go to Quebec City. So I travel about 2,200 kilometers and I fast charge constantly. I have well over 130,000 kilometers on my vehicle. And my degradation is down to 93.6, I think, the last time I checked. So it's really not having a whole lot of impact. Now, on other batteries with thermal management and how they operate, that's where you might see a big difference between degradation. So every manufacturer may degrade a little differently depending on their chemistry, their thermal management systems, and the level their people are charging at.
It all comes down to heat. It all comes down to the heat and how they're managing the heat, because the only difference really from the battery standpoint, or the potential difference in damage, long-term damage that could be done to the battery, is from the heat induced by charging it faster. And if you look at the vehicles that are able to charge the fastest, these are the vehicles that have the most advanced thermal management systems for the battery. So if you look at older EVs that had very little to no thermal management, the degradation goes down, and fast charging them, they would just go.
How do you think I got these cells? I got a whole bunch of cells here from Leaf.
Because in the first gen Leafs, there was no thermal management, or I should
no, that's right.
Truth there, but little thermal management.
Here's another really good question from Johnny Stallings, who works in the HD commercial industrial sector. He said, do you foresee any standardization in the growing EV market similar to the OBD standardization, or will we have to buy a scan tool for each individual?
I hope that someday we're going to see that, but I think that right now, unless you've got other things on the horizon that you're seeing, from what I see is that being an EV, you're skirting or almost skirting all of the current legislation, in that you don't even need OBD. You don't need to follow any of the standards for scan tools or anything like that, because you're not polluting anything. So the legislation hopefully will change so that's in right to repair and emissions guidelines, but hopefully those would change, but I'm not aware of any forthcoming changes to that.
No, because CARB, the California Resource Board, who regulates OBD regulations, especially in scanner use and stuff like that, it's all emissions based. So the vehicle doesn't have an internal combustion engine to emit emissions. Manufacturers are not required to put an OBD connector on their vehicles, and that's why an OBD2 connector, the 16-pin connector I'm referring to, they don't exist on Teslas. So the 16-pin connector does not exist on a Tesla, and you're going to start seeing other manufacturers may revert back to their own types of scanners, especially on the electrification, which could cause us to go back into the OBD1 days, where everyone had their own configuration, their own connector, and so on. So until we see that, but here's a fun fact. If you have a class and you're showing them a Tesla Model 3, ask the students where the federal emissions label is on a Tesla. It has no emissions, has no exhaust, has no fuel tank, no evap system, but there is actually an emissions label on a Model 3. And I don't know about the Ys. I always forget to check the S's and Ys. They're there as well. But on the Model 3, it's actually on the trunk lid under the back lip. So if you open the trunk on a Model 3, you'll see the emissions label on the very back of the vehicle. And so it's it doesn't say anything. It just says federal emissions meets OEM emission or CARB emissions of 2018 or 2019, whatever the year was that you had that car. So
okay, so there aren't any more Q&As. Do we want to talk about when our next one is?
Sure, I think that
Make sure that we have it in the calendar. Yes, it is going to be on February 14th, Valentine's Day. It's a date.
Woohoo!
1 o'clock.
The date.
Wear red,
Perfect.
Jimmy?
Yes, February 14th, we'll spread the word and everything.
Yeah, and we'll probably continue. What I'd like to do is, I like to do one on testing high voltage batteries, like testing, full on testing, the importance of arc flash, testing points, things like that, especially to give more confidence and understanding on the, and maybe even at that time, we may even have the 400 in place too, so.
One last thing, Dave, we had one last comment, and I'm going to lead into it, and you'll know exactly what I'm talking about, is we mentioned earlier a safety incident. I don't want to say where it happened.
Yeah.
We don't need to say where it happened,
no.
To give context to this is that as you get further down into the detail of a battery, okay, there's different levels of danger, and it's kind of, if you graphed it, the danger is little, more, and then when you get down to the cell level, almost none. Like Dave, when you said, when you're past a bunch of the dangerous steps, you could practically put your hand right on the cells and you measure right there, 4 volts, 8 volts, 12 volts, whatever. Nothing too scary, but there's certain steps in the process of dismantling a battery that get potentially very dangerous. And these are things that no technician or shop would do, and no school teaching automotive would do. But if you're researching and going really far into how the battery works and stuff, Dave, I'm sure you've got your leads ready to do the demo.
Oh yeah, yeah. I love safety, so it's kind of right up. And I was like, oh, I wanted to. So what I want to share with you is an incident that came about that was shared with me. And what happened was there was a new student going into a lab, and they were actually testing high voltage batteries, and they were doing a battery testing and so on. And the instructor always has new students wearing all the gear, all the flash protection. They have their processes, procedures in place. So fortunately, they were wearing all their PPE, and it shows you how fast things can happen. And anyways, when the friend of mine that was there, actually, when he saw the flash, and it was extremely violent. There was a bang as well that happened, and fortunately they were wearing all their. Good thing they're wearing all their PPE. I have the arc flash here with the shield and stuff like that, and then of course the coveralls, and they're measured in a calorie. So this one's a 12 calorie, which is a level 2. You can go up to 40 calories, and we can talk about that and how you measure that, and something to share with students. Electricians know this for sure. But what happened was they had all the gear, all the processes, all the procedures. They had everything out, but what they didn't do was the leads. When they went to test the high voltage side of the system, what happened was the leads actually connected in some way. And when the leads connected and you put 400 volts with all that amperage through those two little points, it basically blew the leads apart. So one thing you'll make sure is, like, even though you have all the gear, you're wearing all the PPE, you got your boots, you got your gloves, you have your mask, you have your hood, you have everything, you're in an open battery, or you're even doing testing, and this one here really ensures on the Tesla that you are not going to connect. But regardless, is make sure that if one, and this is the funny part because I see this all the time in kits and that, do you have the proper shield over top? This way, it's impossible for it to touch. There's one for the positive, one for the negative. And then, or you have, these are really cool from Fluke, is that they can actually retract into, oops, gotta get this one back up here. So this way you're only testing at the exact point. So once again, students will forget, especially if they're doing and they're measuring something off and they happen to touch it. If it's high voltage, it can be, there could be an incident with it. So that's why you have your PPE, your arc flash protection. A lot of OEMs do not have arc flash protection as part of their PPE because, in the service side of it, you're not going into the batteries and so on. And that information is written for OEM technicians. So that means that when they're doing their job, they're going through their protocol, they're using their leads. They're probably designated that, don't retract or anything. They're using their specific leads, using their specific meter, and, and they're following those procedures and doing those checks. But, when you're in a classroom and you have many students in that, and you may be using a variety of different meters, following OEM procedures, but once again, make sure you're running the right CAT regulation for the leads, as well as make sure you have the proper leads in the sense for high voltage testing. This is a great way of doing it. On the Tesla there, it's a little difficult to be aware that you need the smaller ends here. Once again, it's Tesla's part number specification, so you can get down and touch on top of that other side of the DCFC contactor inside there, where the other connectors may be a little too big. I think these ones are okay. I have another meter, but some of them may be too big to get down really far in there, which can cause somebody to use an extension, which would not be, which then you're really involving a risk factor in that test. So
somebody had a question about what the yellow shoestring was in your safety slide.
Yellow shoestring.
Mm-hmm.
Slide was that? Oh, I think I might know. Safety. Oh, great. Okay. The big hooks that come with, they call the shepherd's hook for EV safety and stuff like that. The shepherd's hook needs to be certified every 10 years. It has to be inspected weekly, needs to be cleaned. You got to remember, those shepherd hooks are made of fiberglass. If they're in a shop environment, there's lots of dust and there's oil in the air. It collects on that shepherd's hook, and somebody happens to you have to use it. And that shepherd's hook has a conduit on it. It's conductive because of the dust and stuff like that could cause injury. So what this is, these are the coveralls that electricians will, in some cases, use. You don't see a lot of, they have the coveralls, and attached to the back of the coveralls is a Kevlar rope. It almost reminds me when I was a kid and my parents would tie a harness to me and so I wouldn't run away. But don't laugh, Nathan. Anyways, and this harness, so this is really what happens. This is, basically put off to the side. There is a little pocket in the back here, but basically this would be put down somewhere. And if there was an injury, somebody could just grab the yellow shoestring, I like that, and then basically pull them away from that without having to go, where's the shepherd's hook? Where's the hook? How do I get it off? So basically it's already part of the PPE. So,
yeah.
Excellent.
That's a good one.
All right. So we will see everybody again on February 14th. A reminder that it has been recorded. We will be posting the full recording up on our YouTube page, and we'll also share it on our Facebook page.
Yeah.
So check that out on our socials. And we always look forward to hosting you the next time in February 14th, 1 p.m. Eastern time.
And please, just once more, ask everyone, we say this every time, if you could submit your ideas. We want to keep this going month after month. If you have ideas for subjects, if there's areas that you want us to talk about more, let us know in advance, and we'll prepare for future months of this webinar with the subjects that you guys suggest.
Or even if you want to have an open forum, open discussion, we'd be open for that, to try and share and answer some of the questions you have. There might be a lot of conversation that we have no idea about that you might have some experience with as well. So
very good.
Otherwise,
thank you, Dave.
Great. Thank you very much. Everyone have a great day.